our seminar today from Professor Buta of University of Alabama in the United States. This is, as you know, within our series of seminar of people that is going to observe to La Palma, and we invite them to come here to La Laguna and to give us a talk. So it's my big pleasure to introduce Professor Buta, who has a long record of good research. He did his undergraduate on the Casey University in Cleveland. Then he did a PhD in the University of Texas, Austin, under the supervision by the Baculer. And then he did a couple of postdocs, one in the Australian National University and another one at the University of Texas, where he was working at the cell reference catalog. And finally, he has been professor since 1989 at the University of Alabama. He's going to talk today about the quantification of bar strengths and the structure of galaxies. Thank you very much.
Thank you. It's great to be at the Institute of Astronomy here. It's really been fun to visit Tenerife. This is my first time here when I wasn't just passing to go through somewhere else. And I've come from the very hot southern United States to the much cooler area here. So it's interesting to have a break from the heat in Alabama. Now I wanted to talk about bar strength. There's no doubt that barred galaxies are interesting. They're morphologically interesting. They're fun. Bars can be a major perturbation on the disk of a galaxy. So it's interesting to see how you can quantify them. And speaking of Gerard de Vaucouleurs, who was my supervisor, one of the things he was always interested in was to try to quantify morphology, to go beyond conventional classification. So this is sort of related to that. So I'll talk about quantification of bar strength and the structure of galaxies. There's just a few things you might ask, like why would you study the bar properties in galaxies? For one thing, the bars are so abundant, very pervasive. Most galaxies have some sort of a bar. And another thing that's interesting about bars is they're a feature that's in common with between S0 galaxies and spirals. They cross the spiral S0 divide. Well, other things do too, but bars do it in a very, very strong way. You can classify barred S0s, you can classify barred spirals. But most importantly, the bars have been linked to a variety of interesting phenomena, like really interesting circumnuclear starbursts, nuclear rings, resonance rings, resonance-type features. They were implicated to some extent in active galactic nuclei. It's always hard to try and pin down associations between different phenomena, but people have investigated that issue. And finally, bars have definitely been implicated in the secular evolution of the structure of galaxies. It even goes back to the 1970s when Cormody was talking about the evolution of bars into lenses. And now people talk about pseudo-bulge growth. And as if some bulges form by the secular redistribution of material in the galaxy disk due to the presence of a bar. And so secular evolution is actually a very important topic in galactic astronomy. And finally, and probably really interesting too, is that bars have cosmological significance, because if you're interested in trying to determine when the Hubble sequence came into place, you can't ignore bars. They're part of the morphology of galaxies. They're part of the Hubble sequence. And you'd like to go back as far out in redshift as you can to see when did the bars first develop. And so people are interested in bar fractions as a function of redshift. So bars have definite cosmological significance. So this is just a small sampling of reasons why you might study barred galaxies. Maybe there's a few questions you could ask, like how frequent are bars in disk galaxies, and that may be a function of redshift. And also you could ask what determines how strong the bar looks. Some of them don't look so strong. Others look stronger. And you see features associated with bars, and you could ask to what extent do those features depend on the bar strength. Maybe they don't, but maybe they do. And another interesting issue is what's the distribution of bar strengths? If you could quantify it, what is the distribution of bar strengths? Is there some trend in that distribution that might help you interpret the evolution of these galaxies? So that's just a few little questions you might ask. Now, the barred galaxies go all the way back to, barred galaxies go all the way back to William Parsons, the third Earl of Ross, in the 1840s, 50s, and 60s. They could see the bars with the big Leviathan telescope in the center of Ireland. But they were first recognized by Curtis in 1918. Some of them were called phi-type spirals. And of course, they fitted neatly in the Hubble tuning fork as one of the prongs of the tuning fork. And originally, Hubble thought that barred galaxies constituted only maybe 20% of normal galaxies, but that was an underestimate. Now we know that barred galaxies are actually more abundant than the ones in the upper prong of that tuning fork, the ones that are non-barred, to be called normal spirals. So anyway, that's the first look at how they fit into the morphology of galaxies. And then de Vaucouleurs, on a cloudy night at McDonald Observatory around 1962, didn't have anything to do because in 1962 we didn't have the internet. So if you're at an observatory and it's cloudy, you couldn't log in and do your work back home. You just really had to find something to do. You go to the library. He made this sketch in around 1962 showing barred and ringed spirals around stage SB. And you see in the barred galaxies, you see the ring variety, the SBRs, and the S-shaped variety, and the pseudo-ring galaxies, RS. Let me see if I can point this here. See these right here? And it's a very interesting look at galaxy morphology. And also what's nice about this is the bars are represented as continuous features of morphology because, you know, you've got this SAB category. Hubble and Sandage, they did recognize the intermediate class, but de Vaucouleurs made it part of the classification system. It was a good thing, I think, the SAB class. And of course, they make lovely pictures, barred galaxies, going all the way from the S0 types here to the early type spirals, to the intermediates, to the very, very late type spirals. So you can't avoid bars in almost any part of the Hubble sequence. You're going to have to face them. They're there, and they get more asymmetric as you get towards the end, towards the late part of the Hubble sequence. But they're very important, and they cross the spiral S0 divide effortlessly. Now, de Vaucouleurs considered, as I said, bar strength as a continuous property from the non-barred galaxies here, the SAs, to the intermediates, to the conventional SB galaxies. And, you know, this is cute here. The SABs and NGC 210, the bar is just an oval, and it's worth recognizing ovals as bars. They're bar-like perturbations. They may not be exceptionally strong, but they're nevertheless there. So ovals are important, and probably the de Vaucouleurs classification maybe brought more attention to that, and people appreciated them more later. So there's ovals and bars. They're bar-like features. Now, if you wanted to study bar strength, there's a few samples you might use. The really great Ohio State University Bright Galaxy Survey, where they, in the 1990s, took images of optical and infrared images of a reasonably good-sized statistical sample of galaxies. And the early type analog of that, because the OSU BGS is mostly spirals, the early type analog of that is the near-infrared S0, which is a survey I've been involved in. Covers just the early type galaxies. It even goes to S0A, SA. And I take S0/A very seriously. It used to be considered a garbage dump in the Hubble sequence. It only depends on whether you put the garbage in there, but really it's a well-defined type. So the near-infrared S0 survey also includes S0A and SA because Those are the transition types. And people have used these samples to look at Fourier properties of bars in the context of Athnasoula's models, and look at bulge properties as a function of Hubble type. And it's been fairly interesting. Just from that OSU BGS sample, I just want to say when we talk about almost all of this is really biased. It's biased towards galaxies of high luminosity, absolute magnitudes minus 18, minus 22, with an average of minus 20. We're not talking about the dwarfs. And bars are more pervasive among the dwarfs, but they are not necessarily what this is all about so far. The dwarfs still remain to be analyzed in this way. So we're talking about high luminosity galaxies, at least as luminous as the Large Magellanic Cloud in M33, with an average absolute magnitude close to that of the Milky Way. Now, one of the issues you might look at is the frequency of barred galaxies. There have been a lot of papers about this, and people settle on a frequency of about 2/3 of these luminous galaxies have some sort of a bar. But I picked one here based on the OSU BGS by Eskridge et al. They had the H-band, and it's good to go to the H-band because it penetrates the dust, and you can see the bars a little bit better. And de Vaucouleurs was always good at detecting bars when other people didn't see them, but even he missed some invisible light. And the paper talks about the ones that even he missed, and it's hard to imagine that he missed a bar, but he did sometimes. But 186 spiral galaxies in the H-band, and they visually classified the bars on the images and found that 56% were, quote, strongly barred, 16% were weakly barred, and 27% were non-barred. Well, I think one of the interesting things about this was that so many stayed non-barred. They didn't all the blue light non-barred galaxies didn't change into barred galaxies. A good number stayed non-barred, which was interesting. But one point I wanted to make was that even if you go into the near IR, even though you can see the bars better, it doesn't mean that the rankings of the bars have changed. Now, and I'm showing here what I mean by this. Now, there may be a galaxy that in blue light is classified as non-barred, but in the near-infrared you see a bar, and so you could recategorize it as, say, S capital AB. Now, you could see an S capital AB weak bar in blue light that in the infrared looks stronger, and so you call it a stronger bar. But an already SB galaxy in the infrared still looks like an SB galaxy in the infrared, so it has no new category to go into. And so you get this type of thing, where they all more look strongly barred, but really the rankings haven't changed. A weak bar in blue light is probably still weak in the near-infrared, but it looks stronger. But the strong bars in blue light look even stronger in the near-infrared, but they don't have the new category to go into. So the rankings, I don't think, change. And there's a few other papers that discuss the issue of bar fraction. So it runs about 65% is what the consensus, and it may depend on whether the galaxies are active or not. Maybe active galaxies might have bars more frequently or not. There have been studies of the bar frequency as a function of redshift, and here's one of them. I mean, here's just one highlight. I'm no expert on high redshift galaxies because I haven't personally studied them myself. But of course, people are interested in the bar frequency versus redshift. Maybe it's 2/3 nearby. And what was it at z equals approximately 1? Now, there were a few papers here that suggested the bar fraction was constant to about 1. So that you might think that the Hubble sequence or the Hubble types were roughly in place by then. But then there was this more recent study by Sheth et al. Here using Cosmos 2, which I think is probably an ACS sample. And I've seen the images, and they're really great, and I can't wait to look at them myself. But I've only looked at a few, and I've seen familiar types by doing that. But when they analyzed it, they did visual analysis. They also did, I think, ellipse fitting type analysis to determine whether there were bars present, and calculated the bar fraction as a function of redshift, and it seems to drop. I believe that over the whole sample, they had maybe 65% nearby, dropped to 20%. But among the strongest looking bars, they were 30% nearby, dropping to 10% far away. But they concluded that the most massive galaxies had already developed their bars more quickly and had a comparable fraction to now. And so now the bars have shifted to the lower luminosity galaxies, the downsizing type effect. And in fact, you look at low luminosity galaxies and bars are very abundant. But nevertheless, they're the ones that haven't been the subject of too many bar strength studies. We focus on the interesting early types because they're a lot of fun, and they're also easier to deal with probably. Anyway, you can ask what determines the bar strength of a galaxy. Now, Anthony Zula has done some really nice models. It really depends on the effectiveness with which a bar can transfer angular momentum to other components. So the other components could be the halo, and it will depend on the properties of the halo, how effective that is. But if that would be in a relatively closed system. Galaxy components can interact. In fact, Cormandy in the late 70s had already suggested that was possible when he had a bar evolve to a lens that involved an interaction with the bulge in his point of view. So it makes sense that if it's an isolated galaxy, there could be an interaction with another component. But the issue of an open system allows external gas accretion to influence whether a bar can be destroyed and whether it can be regenerated. If you cool the disk enough by gas accretion, you can regenerate a bar, which certainly makes the barred galaxies even more interesting, I think, if they can disappear and then return, because if a bar disappears in a galaxy, there may be stuff that the first bar generated when it was there. Then the bar disappears and a new bar forms, and it's in the presence of this other stuff. And so it may impact what we see. One way to quantify bar strength is with bar ellipticity, and I show this plot on the left here from Abraham and Merrifield. This was one of the first looks at some of the correlations, quantitative estimates of bar strength versus other things like the concentration of the galaxy. And that's what, this is a nice picture they made with little postage stamps, images of all the galaxies. And they plotted a bar ellipticity parameter here. It's not exactly the bar ellipticity, it's just a representation of it that spreads out the points, spreads out the numbers in a certain way, versus the concentration parameter. And they found the strongly barred ones up here and the weakly barred and non-barred ones here, and there was a little bit of a gap, and it suggested there might be rapid evolution from the strongly barred ones down to here, because it was always expected the bars would weaken, not necessarily strengthen. But there would be a rapid evolution, and so that gap was an interesting find. Now, of course, people have looked at this again. Here's a very recent study by Marinova and Joji. I don't know how to pronounce her name. It's either Yogi or maybe it's Yogi or Joji. Pardon? Jogi? Jogi. They calculated a similar bar ellipticity parameter and didn't find evidence for a bimodality. And so it's not clear that this evolution is still there, but this may have been, I think this was based on a sample of images obtained by Fry et al., and maybe it wasn't quite statistical. But in any case, the bimodality isn't confirmed there. Now you can do Fourier analysis because, of course, Fourier analysis is perfectly suited to studies of these non-axisymmetric features in galaxies, and you can just take the intensities, the relative intensities of the Fourier components, Im over I0, that's the intensity of the mth component relative to the zero-order component, the m equals 0 component. And here I show the profiles for m equals 2, 4, and 6, and the same thing for this galaxy here. And as a measure of the bar strength, you could, for example, take the amplitude of the m equals 2 term here, which is called A2, and this is an SBA galaxy, and that's an SB0. And you can call that a measure of the bar contrast. But it isn't necessarily the bar strength, because really the bar contrast maybe doesn't tell you how influential the bar actually is. It's just how bright it looks relative to the background. It's an intensity, a relative intensity measure, but you can use it as a measure of bar strength. And Atmasula uses this as a measure of bar strength. She calculates for her models in mass Fourier, the relative Fourier profiles of the mass. And so this is the same as what I just showed you in intensity. Here's m equals 2, 4, and 6, and here's even 8. And she calculates these profiles for her various models, like a model with a massive halo but no central mass concentration has a profile that looks like that. Profiles look like that. And here's one that has an increasing central mass concentration here. And you'll notice the profile goes from being asymmetric to fairly symmetric. And of course, this is something this is a way you can compare models with observations. The bars are very amenable to this type of thing. And so if these Fourier mass profiles can make this distinction, maybe the observed ones could too. And this is from this particular paper. And just going back to the profiles I already showed you, one thing you find, like in these real galaxies, NGC 1452 and NGC 1533, you can get rather different looking profiles. This one looks an awful lot like the Atmasula models with a massive halo but no central mass concentration. Whereas the one down here looks a lot more symmetric. It may have a central mass concentration. And these profiles can be fitted by single Gaussians, which I don't understand, or double Gaussians, but they still look like the Atmasula models. So maybe comparisons like this are another way to evaluate those models. It certainly looks worthwhile. I think she's certainly got something to say about this type of profile. Massive halo with no central mass concentration to weaken the bar. But is that the case in this galaxy? We don't even know anything about the halo in either of these galaxies, but in principle it could be learned by further study of those galaxies. Now, another way to quantify bar strength is the gravitational torque method. This method takes a near-infrared image, and you assume that the near-infrared light traces the mass, which is probably, it's a better assumption for near-infrared images than it would ever be for optical images, because in the near-infrared, the extinction is reduced. You're looking at a largely old stellar population. It can't be a perfect assumption in any case. I mean, it's an approximation. It can't be a perfect assumption. But given this assumption of a constant mass-to-light ratio, and you can even make corrections for stellar mass-to-light ratio differences using the colors. But even if you ignore that, you make a constant M over L assumption, you can convert the near-infrared image into a potential. From that potential, you can calculate the tangential forcing in the disk and the mean radial force in the disk that determines the axisymmetric rotation curve. And you can calculate what's known as a ratio map. Q of ij is just a tangential force at pixel ij divided by the mean radial force at pixel ij. If you do this in a Cartesian coordinate system, and then you can define the Q sub tangential, Q sub t, looks like Q sub tumre, but the t there means tangential. There's also a Q sub t. That's the Q parameter, the tumre Q parameter. That's not what I'm talking about here, so maybe it's a bad choice of terminology. In any case, it's called a ratio map, and QT of R, I mean this is a ratio map. QT of R is just a graph of the maximum of that ratio as a function of radius. And here's a variety of papers that talk about this method called the gravitational torque method. And it's interesting to calculate these maps and see what you can see how to use them to quantify bar strength. And that satisfies the Volcker goal of quantifying galaxy morphology. It's not the Hubble type, it's just the bar. But the bar is very amenable to this. Now, what is this tangential force ratio measuring? In this picture of a solar system orbit, because most of the mass is concentrated in the sun, the force is radial for a planet orbiting the sun. But in the presence of a bar, you get a tangential force due to the extended bar here. And you can quantify the bar strength by the amount by which the force here is not pointing exactly at the center, but is offset slightly towards the ends of the bar. The stronger the bar is, the bigger the offset that you would have here. So that's a way of quantifying bar strength. And you can do it by this force ratio, because it's going to be the same thing as a measure approximately of that angle right there. So that's how you can get bar strength from forces. And you can make very colorful force ratio maps. Here's the lovely galaxy NGC 6951, and here's its force ratio map. And you see these 4 islands here are areas of maximum tangential forcing. And you get 4 quadrants because the sign of the tangential force changes as you go in azimuth around. And in fact, the tangential force is going to be pointed towards the ends of the bar. And so as you move around, it's going to have to change sign. And so you get 4 islands. And you can divide the galaxy into 4 quadrants. And you want to know the maximum. What you'd like to get out of this is you want to take this complicated-looking thing here and just get one number out of it that you can say, the bar strength. Just one number is all you really want, because you don't want all those numbers. So what you do is you divide the galaxy into quadrants, and you map out in each quadrant the maximum, the absolute value of the ratio. And then you take an average of the maximum at the same radius in each of these 4 quadrants. And when you do that, you get a graph that looks like that, the QT of our plot. See here? And then you can read off the maximum of all the maxima as a function of radius. And that's called QG. And that's the maximum gravitational torque per unit mass per unit square of the circular speed. And you can call that the bar strength. Or more accurately, it's the non-axisymmetric torque strength, because there's a spiral in this galaxy too. And that's why its force ratio map looked complicated, because it wasn't just a bar. It was a bar and a spiral. Well, now, having so quantified the bars, you could look at the distribution of bar strength, because this Selwood paper was published in 2000, but I heard the talk in 1998, and Jerry Selwood was having a crisis of confidence, I think. For a long time, people believed that bars formed by the so-called bar instability, the natural instability of a galaxy where the amount of kinetic energy in ordered motion is significant compared to the amount of kinetic energy in random motion. So you have the bar instability. And he said the frequent presence of nuclear rings in galaxies suggested that there were inner Lindblad resonances present. And that threw a damper on the idea of the bar instability as being behind bar formation. Well, I've communicated with others who still think the bar instability is the issue, because you can do simulations that show it. But in any case, one of the nice things about Jerry's paper was that he mentioned the distribution of bar strengths. That's something you could try and determine observationally. It may help sort the issue out. Anyway, that was one of the things that inspired me to do bar strength work, was that paper. Anyway, you can look at the buildup of central mass concentration and bar destruction. Bars are not necessarily going to be forever. They can evolve. The buildup of a central mass concentration can weaken bars. And then they can reform by gas accretion in that Bornaud and Combe 2002 paper. Tidal interactions can be involved in regenerating bars. It's already been known from Noguchi's work in the 1990s that interactions may have a role in bar development. And finally, the pseudo-bulge and lens formation work of Cormandy and Kennicott is all relevant to this bar strength issue. Now, here's a paper which uses a couple of the bar strength parameters I just told you about. The QG is on the left, and the bar contrast A2 is on the right. And it shows the correlations between the QG, A2, and a normalized nuclear velocity dispersion. And the issue here is how does the hotness of the central component connect to the bar strength? And there's, from both plots, there's a suggestion from this paper by Das et al. That galaxies with hotter components have weaker bars. Hotter central components have weaker bars. Or perhaps they are weakening as their components, their central components evolve and they get hotter, and that may weaken the bars, and that's another way to affect the evolution of bars. So there's a possible correlation like that implied by these bar strength indicators. And here's another issue. You can look at those relative Fourier amplitudes I showed you where there's a peak, and the peak occurs at a given radius, and you can call that radius r sub 2. So let's see here. R sub 2 is the radius of the m equals 2 peak. So you have those Fourier profiles, Gaussians or double Gaussians, and there's a peak, and there's a radius associated with that peak. So that's called R2. And R25 is the radius of the de Vaucouleurs isophote 25 magnitudes per square arc second in blue light. I wouldn't use capital R25 for that, but that's what was used in this paper. Anyway, R25 is a radius, but in RC3 it's an axis ratio. It's meant to confuse people. It shouldn't, but it can. In any case, for a sample of about 23 barred galaxies, and this is with something that Johan and I were working on too, there's a correlation between the amplitude A2, the peak, and R2 over R25, the relative radius, implying that long bars have higher contrast. And apparently it hadn't been noticed before, but long bars have higher contrast. And people, in this paper, they went back and looked at other samples and found a similar correlation as given by these 23 new galaxies. And this paper also analyzes these 23 galaxies by calculating an approximate central density and showing that approximate central density also correlates with this ratio. And the longer bars have a higher central density. So the implication is that if you expect that denser galaxies evolve faster, then that can explain this. Denser bars evolve faster, the bars get longer, and it shows bar evolution over a Hubble time. But it doesn't necessarily tell you the bars have dissolved and reformed. The bars evolve over a Hubble time and get longer. That's what this shows. And here's something that I thought was interesting. Getting back to de Vaucouleurs, going back to the 1980s, when people were doing these one-dimensional photometric decompositions of galaxies. This here is a plot. Let me see. This plot right here shows the bulge to total light ratio as a function of Hubble type, coded on the RC3 numerical scale. And so on this scale, these are the S0s. These are the early type spirals. These are the late type spirals, and these are the irregulars. And back from those one-dimensional fits, the bulge total light ratios got pretty large in the S0s. But with modern two-dimensional decompositions that allow you to account for bars, lenses, and other components that had to be ignored in the past, the bulge to total light ratios have come down in the S0s. In fact, at all types, they seem to be lower, except here where there weren't any bulges in the first place. But in any case, let's see. You do have higher bulge total luminosity ratios in S0s, but they're not nearly as high as they used to be. And here is the Sirsic index, because back when this was done, the bulge was always characterized by the R to the quarter law. That's fallen out of fashion. People use the R to the 1 over n law. And here's the Sirsic index n versus Hubble type index. And the Sirsic indices are all averaging below 2. And it seems to satisfy that Cormandy and Kennicott definition of a pseudo-bulge. Now, a pseudo-bulge is different from a classical bulge. Classical bulges are supposed to form by mergers, early mergers, and approximately follow an R to the quarter law. Pseudo-bulges came later from disk secular evolution, and they would have they would be more exponential. And an exponential is 1, and here's R to the quarter, And you see they're closer to exponential. So it seems that most of them, even across the whole Hubble sequence here, that's in this paper here, they seem to be pseudo-bulges. And now pseudo-bulges are bulges, and classical bulges are really, well, when the false bulges become most of the bulges, are they still pseudo-bulges? Well, anyway, and then this here shows that the mean total non-axisymmetric strength, QG, is lower for the early types. So by that bar strength indicator, the early types, which have such great-looking bars, they look so strong, they look so well-developed, their bars are not that strong because they're in the presence of a stronger bulge. The bulge is very important in bar strength estimates because that ratio map was the tangential force divided by the mean axisymmetric background force. If there's a bulge, the mean axisymmetric background force is going to be large. And so the force ratio is going to be small. In early types, if there's a bulge, a significant bulge, which there is usually, and so the bar strengths are going to be weaker. Now, this is counterintuitive to what you would guess just by looking at the images. Maybe you can't tell the precise bar strength of a galaxy just by looking at its picture, which may not be surprising. But in any case, you see here that the late types tend to have the stronger bars. But the late types are the ones that haven't been studied effectively, because to get the bar strength, you have to assume a vertical scale height, and maybe it's hard to know it. There can be some really thick galaxies in these late types. So the late types are still an open question, but there seems to be weaker bars at early types, stronger bars at late types. Now you can analyze these gravitational torques. You can do a quantitative dust-penetrated bar classification, which may be useful. You can look at the distribution and type dependence of those QGs for this sample. You can look at active versus non-active galaxies because, of course, people are interested whether bars have something to do with activity, and maybe there's a correlation with bar strength. And that's been investigated by, it's not just this paper, there have been other ones as well. And I'm not going to talk about all these things. Bar strength and inner ring shape has always been something I've been interested in, and you can look, and then you can have a little bit more, you can do a little bit better, because that QG includes spiral arm torques. You can try to separate the bar and the spiral. You can have fun doing that and see if it's even possible to do it, but you can certainly do something to separate the bars and the spirals if you want to look at real bar strengths and not bar plus spiral. So those are just a few things you might do. And here's the quantitative bar classification from this paper. And here's a picture of NGC 1433. Here's the force ratio map. And these little white squares are the maximum points, which I superimpose on the actual image. And you see that these maxima are just inside the ends of the bar. And so you can calculate the value in the map here at each of those points. Take an average and you get a bar strength. And here I start with a non-barred galaxy, showing the points are quite spread apart in the square because there's no bar there. And then they get closer together to the bar as the bar gets stronger, until you have a really strong bar when the maximum points are really touching and hugging the bar. And the reason they go from being very open like this to very tight like that is that these bars have a more significant higher order terms. And that brings the points closer to the bar. So you could use those points. You could use how close they get to the bar axis as a measure of, as a quantitative dust-penetrated classification. These are all near-infrared images. And then there's the case of now bar strength and inner ring shape. Now, theoretically, it's easy to explain inner rings. And here are some rings. You see a bar, and here's an inner ring, and here's a bar, and here's another inner ring. And then you have a bar, inner ring around it, and the same thing there. But these are deprojected images. And you can't really deproject a galaxy perfectly, but you can do an approximation. You just measure the shapes of faint, dim outer isophotes, and you use that to assume they're intrinsically circular, and you deproject the galaxy. And here I've deprojected them, and I've rotated the bar horizontally so we can compare them. And you see that in these deprojected images that the rings can have a wide range of shapes. Some of them deproject into circles, and some of them deproject into ovals. They can even be pointy ovals, which is interesting. So you can already see there's a wide range of shapes. Now these numbers here, this is the d-projected axis ratio of the inner ring. So this one's about 1/2, and that one's about 9/10. That one's quite circular. This one's 0.66. That one's almost circular also. And now for each set of these red images, there's an H-alpha image that has also been d-projected the same way. And look at how the H2 regions know the shape of the ring. They care about it. But do they care about the bar strength is the other question. Now here you see that the ring, the circular ring, the H2 regions, are relatively uniformly distributed around the ring. But here, they bunch up at the major axis, which is the bar axis. Here, this is a circular ring, and there's little azimuthal variation in the H2 regions. But here you get a colossal effect. And the pointed oval shape has H2 regions bunched up around it. They care about the shape of the ring. But now, in these left panels here, this is the QG bar strength. And so you see these galaxies have approximately the same bar strength. But their ring shapes are very different. So the first impression is that the shapes of these rings don't really care about the strength of the bar. I don't know if that makes any sense to me. They ought to care. If this is a real measure of bar strength, they ought to care, but they don't. So that's an issue that needs further investigation, in my view. Now here's a little bit of this is a further study of the previous slide, where this is my student Rebecca Grouchet. She looked at star formation rates in inner rings because you saw the H2 region, so you can isolate the ring and you can get a star formation rate in solar masses per year. And so these are the star formation rates in the rings and solar masses per year against a variety of parameters. For example, the d-projected shape of the ring here, and the filled circles are barred galaxies, and you find rings in non-barred galaxies. They don't have to have a bar. So that's another issue. How do you get a galaxy with a ring and no bar if theory says you need a bar to get a ring? There are non-barred ring galaxies. They're hard to understand. They may be connected to the evolution of bars. But as far as star formation rates are concerned, in general, they're in the same range. The bars are not causing enhanced star formation rates in these rings. They may not even be causing the star formation in the first place. They may just be gathering the H2 regions into these resonant orbits, but they may not necessarily be at the heart of the star formation process in the rings. And down here, well, at least that's what I might gather by looking at a plot like this, where the d-projected shape of the ring doesn't matter and the bar strength doesn't seem to matter. But, you got points out there because maybe there's small number statistics. There are clearly some exceptional cases like that one. But here is a plot of the d-projected ring axis ratio versus the bar strength. And I just said that there was no correlation, but when you put together a large number of galaxies, those with bars and those without bars, you sort of see that there isn't much correlation, but maybe you could follow that and say there could be something. But then you look up here at round rings, and there's a wide range of bar strengths. So there's a reason that there may be two different things we're seeing in this plot. And when they overlap, they give you the impression that there's no correlation, but maybe there's two different things we're seeing. Why are there round rings around bars? I'm still not sure about that. But you see them in theoretical models, round stellar rings. But in any case, that's just an interesting aspect of bar strength and rings. And I think these are cute. Bars have really interesting morphology. They're not just bars. They can be bars plus ANSEI. And these are ANSEI-type bars that Inma and Johan and I did a little paper on this. And these are some unsharp mask images of ANSEI-type bars. This is NGC 7098, and this is NGC 7020, which is crying out for further kinematic analysis. Both of them are. They're just crying back out at us for further study because they're interesting cases. Look at the ANSEI are these enhancements at the end of the bar. Sometimes they look like this, sometimes they're just spots. This here area looks an awful lot like some of these boxy bulge edge-on galaxies, but that's not an edge-on galaxy. Why does it have ansae? I'm still not sure about it. But in any case, these ansae may be related to how bars grow, and in the paper we find that the ansae bars tend to be stronger than the ones without those ansae. But we're still trying to understand how you get features like this, and why this one ansa is wavy. I don't understand that. Now, let's look at the distribution of maximum relative bar torques. This is an issue that Ronald and Combs' paper on bar dissolution and regeneration had something to say about. They examined the impact of external gas accretion. The idea is a bar can transport gas to the center, build up a central mass concentration, and that can weaken the bar, and it can dissolve. But if the galaxy accretes gas from the outside, that can cool the disk, and it becomes unstable to a new bar. And so you get bar regeneration. And if you focus on the distribution of bar strengths, it would tell you the relative amount of time that a galaxy spends in a different bar strength state. The time it spends as a strong bar, and as it evolves, how much time it spends as a weak bar. So it's really an interesting point of view. It makes you want to get the distribution of bar strengths to investigate this. And you can examine this observation for samples of spirals and S-zeros. And here's just it's hard to see, but here's just a couple of models of spirals. The upper panels show the evolution of a spiral with a bar with external gas accretion. You start out with the disk, it has a bar, but over time, gas transport to the center as you go here to here, the bar gets a little bit weaker from buildup of central mass concentration. But then there's gas accretion, and the bar gets stronger. So it gets regenerated. It doesn't necessarily go away, but it gets regenerated. It goes from strong here to weak here to strong again. But without external gas accretion, the same model, the bar is here, it eventually dissolves into a lens, and it never reforms another bar. And so you go from a galaxy that was once barred to a relatively non-barred one, and it never becomes a barred galaxy again. But this one here can become barred again. So in another paper, these authors calculated the distribution of QG values for a sample of models as compared, and they want to compare it to a sample of galaxies, the Ohio State University Bright Galaxy Survey. So the observed distribution of this parameter for the Ohio State survey is given by this. The main things to note about this are the deficiency of weak bars here, low QG values. Now, a QG of 0.4 means that the tangential forcing is 40% of the background radial forcing. So that's a large, strong bar. So these are the weak bars here. And then the dashed curve histogram is for a model with gas accretion, and the dotted histogram is for a model without accretion. So without accretion, you expect a lot of weak bars and less of a tail. But with accretion, you expect fewer weak bars and an extended tail, and so the comparison suggests that maybe there is gas accretion. Now, these QG values are affected by spiral arm torques, and that's a criticism of this. It's not just bars, it's spiral arm torques. But in any case, it could be what this is saying is that the amount of time that a galaxy spends in a strong bar state is a lot less than the time it spends in a weak bar state. So on the whole, we see relatively weak bars. Now, if you want to get at real bar strengths, not just total strength, that's bar plus spiral, you have to do bar-spiral separation. You can have fun with this. You just use Fourier techniques to separate the bar from the spiral. You can make plots of the relative Fourier amplitudes versus radius r, and then you make an assumption that the relative Fourier amplitudes of a bar rise to a maximum the same way as they decline from that maximum. That's called the symmetry assumption. And then you can construct bar plus disk and spiral plus disk images. And so you start out with like an m equals 2 Fourier profile of a bar for this galaxy in the K band, K short band. And here's m equals 4, and how in the world do you use this for anything? Well, the bar is in this area, and you assume that the bar declines past the maximum here the same way that it rose. And you do that for m equals 2 and 4. And that's the symmetry assumption. And when you do that, you can take the galaxy which had a bar and a spiral, and you're left with a bar plus background disk and a spiral plus background disk. You've separated the two features. Now, the spiral is in this image, and the bar is in this image as an axisymmetric feature. All you've done is eliminated its tangential components. And so you can calculate a force ratio map for the bar and for the spiral, and you can map out the maxima in each quadrant, and you can calculate the different curves. So the total non-axisymmetric strength is QG, which we already saw, but you can do one for the bar and one for the spiral, and you can call the maximum for the bar QB, the maximum from the spiral QS. And so now you have quantitative measures of both bars and spirals. So we'll call QB the bar strength, QS the spiral strength, and when the bar is strong, QB is approximately equal to QG, but when the spiral is strong, QS is approximately equal to QG. But a lot of the time, you can use QG as a bar strength measure. Now you calculate the distribution of QB, not QG, and you get lots of weak bars here. There are more weak bars. In fact, it's just a nice smooth decline. Does it still support gas accretion? It might, because that block it all paper, they didn't do bar spiral separations. I don't really know if this still supports gas accretion. It probably could, because there's still an extended tail, and that tail was one of the signatures of gas accretion. So it sounds like it still supports it. But more bars are weak. Most bars are very weak. In this particular study, we've plotted we wanted to know whether the bars drive the spirals that are in them. For example, if you have a strong bar, is it responsible for the spiral that you see? And if the bar is stronger, is the spiral stronger? Is there a correlation between QS and QB? Now, that's a risky thing to do because when you saw the plot of the QB and QS, they had to fit within that QG curve. So if you overestimate QB, you're going to underestimate QS. You're not free to, there can't be any values. So when you make a plot like this, you do have to worry about correlated errors. In a new sample of AAT data, QS versus QB shows virtually no systematic trend. That is, even a strongly barred galaxy can have a weak spiral, but they're still spiral galaxies. In previous studies, there was a suggestion that there might be a correlation, like this is from a couple of papers here. You have weak bars here, and then there was a tendency for the spirals to maybe average a little bit stronger, as if the most strongly barred galaxies were driving their spirals. And when you combine the samples of this and these, you get something here, and you can compute averages, and there's still a little bit of a trend. But it's not clear that you can say that the bars drive the spirals. In the weak bars, they're not driving any spiral. And it's not clear that the strong ones are even doing that as well. That would mean the two features are separate features. They're independent instabilities. Is this a bar-driven spiral? Now, this here shows a new method of calculating the location of co-rotation in galaxies developed by Zhao-Lei Zhang, mostly, and I worked with her on comparing the method with observations. It's called the potential density phase shift method. And in this method, you take a near-infrared image and you call that the density, and then you derive the potential from the near-infrared image, and then you analyze the phase of the maxima in the potential as a function of radius. And then you look at the difference in phase between the potential and the density at the same radius. And that's what this number here is. It's called the phase shift. The phase difference between the potential and the density maxima. And if the perturbation has no skewness at all, there should be no difference. But if there's some skewness in the perturbation, you get a phase shift difference. And her argument is that if you look at the phase shift as a function of radius, that where it crosses 0, that's the location of co-rotation. Now, wouldn't that be, that's an interesting way to locate a very fundamental parameter of galaxies, the location of co-rotation. It's a very important parameter. It affects how angular momentum is transferred from the different regions of the galaxy. Now, if this is the location of co-rotation, there could be more than one co-rotation in this galaxy. And I just said from the previous plot that it didn't look like the bars were driving the spirals. And yet, in this plot right here, there's one crossing, as if there's only one co-rotation. And if there's only one co-rotation, there's only one pattern speed. And so this bar and this spiral, and here's the co-rotation circle, would seem to have the same pattern speeds, which suggests that that bar is driving that particular spiral. But other plots don't look like this. Other plots have many crossings, and it's harder to interpret them than this. But surely there could be bar-driven spirals, and this could be one of them. Now, this one also satisfies our preconceived notions. The preconceived notion is that bars never extend outside their co-rotation circle. And you see here, this one here neatly satisfies that. It doesn't go outside its co-rotation. Now, that doesn't mean that they all do that. For some of them, when you do this, the circle is inside the bar ends, and that's hard to understand. But in this particular case, it satisfies what we expect. So that may be a real bar-driven spiral. Now, just briefly on gravitational torques in S0 to SA galaxies, we did the near-infrared S0 survey, 200 S0, S0A, and SA galaxies, to have a sample similar to OSU BGS. And we did decompositions to get the bulge disk parameters. Here are some S0 and S0A galaxy deprojected images. You see the bars are very, very fine. And here's some of the lovely force ratio maps there. And here's the main plot. Here's the plot I already showed you of the distribution of bar strengths QB for OSU BGS galaxies, showing all the weak bars. And the NERSAW sample broken up into S0s and early type spirals. The S0s show no extended tail. They certainly don't seem to support external gas accretion. They're not accreting any gas because they don't have a tail. But these early type spirals can have star formation, and they have an extended tail here. So maybe the S0 bar torques are, maybe the reason the S0s look different from this is partly due to the dilution of the bar torques by the bulges. But and also there are larger vertical thicknesses, which also affects the bar strength. But in any case, you do not see a tail. You don't see that signature for external gas accretion. In conclusion, the gravitational torque method, it's a promising, but it's not necessarily the best way to do it, but it's a promising way to do it. It has uncertainties. You need the vertical scale height, and you still make the assumption of constant mass of light, but it's still a useful way of quantifying galaxies. You can represent these classifications as a continuous sequence of increasing bar strength. I showed you that these are well-defined parameters. And the distribution of the non-axisymmetric strengths QG for spirals favors external gas accretion, but I'm not sure about QB. It may also. The distribution for S0s favors no accretion. Bars and spirals may or may not be. They may be independent features, but not in all cases. And finally, on average, the early Hubble types have weaker bars than the late types. Well, in any case, I hope that this has helped at least highlight some of the interesting things that you can have, things that you can do with bar strength in galaxies. Thank you.
Okay, thank you very much for an interesting talk. It's time for questions.
Yeah.
Well, you have talked about you saw those maps of the torque in which we saw the maximum of the ratio of radial and tangential forces, and how they were close to the bar in some cases.
Yes.
But is it interesting? Does it have any interest to see whether there's any change, if there is, in the radial position of those maximum relative to the extent of the bar?
You mean like a model of some sort, or?
No, I mean you have been talking about the maximum value of QG, but not much about the radio position of that maximum.
Yes. That the paper by Elmagreen et al. 2007 looked at that very question. They found that the radius of the peak A2, which is going to be close to the radius of that maximum, is larger relative to the disk for the longer bars. And it may have something to do with just the evolution over a Hubble time. But they have been looked at. It's not just the bar strength, but that radius. It is an important issue. It's been looked at. And there's a correlation between the amplitude of the bar and the relative size of the relative position of those radii. Yeah.
Any other question?
I'm not sure if I understood what you said when showing the plot of the frequency of bars versus distance versus redshift, right? So you said there that apparently there was the number was decreasing as you go farther.
The histogram of the bar strength?
Yes.
Yes.
And also, and there you mentioned, or I understood that you mentioned, that it may be a problem with the downsizing. So, meaning that
I'm sorry. You mean the Sheth et al. Study? Yes. Where there's a declining bar fraction. That's what you're talking about.
So what you said was that it may be that what we are seeing far away is just the brightest part of the sample, and because of that, we see it apparently decreasing in the percentage, and maybe that it happened the same as the similar plots with, for instance, the star formation rate, in which when you make a segregation taking different masses into consideration, for low masses things, the plot is more constant than what you have shown. Is that what you have said? I mean.
This is the paper by Sheth et al. I wasn't involved in it, but I'll just tell you what they said about it. They said that 65% of, if you take SAB plus SB galaxies, you get 65% fraction of those at low redshift. That drops to 20% near Z equals 0.8. But then if you select the stronger looking bars, like SB, S capital Bs, they have a 30% frequency at low redshift that drops to 10%. But they also had information to judge luminosities and masses, and they found that the bar fraction among massive galaxies at high redshift is the same as the bar fraction nearby, and that there was a suggestion that there was downsizing in the bar frequency because of that.
Yeah. Any other question?
Yeah, I'm very curious to see, since in the last years is appearing evidence of the presence of inner disks. Is any statistics
of inner disks
you are aware of, or
people like Peter Irwin study these inner disks and inner features? There's no doubt. Yes, there are inner disks, because Cormandy had already found things like that in the 1980s. And an inner disk could be unstable to its own little bar. I mean, I haven't talked at all about secondary bars, but the bars I've talked about are just the bars, the ordinary run-of-the-mill bars that we all familiar with. But in the middle, you can have a secondary bar. You can have a disk that is also unstable to the formation of a bar. That bar would not have necessarily have the same pattern speed as the main bar. And I think there are even galaxies that have up to 3 bars, but I don't know how reliable, the identifications. But the inner disks are going to be related to that. But you can just have an inner disk but no bar, but they're still there. And probably I don't know the statistics of them, but Peter Irwin has studied those. It'd be worth looking up one of his papers.
3 bars and a ring as well. I'm not sure whether it's a disk in it.
Well, as I also understand it, Sebastian here has found multiple nuclear rings in galaxies. They're not necessarily associated with their own little bar, but I would love to see one if there was. But the structure in the middle is the centers of galaxies that can have a lot going on that can be somewhat decoupled from the other parts.
Any other question? Okay, if not, I have just one. So the fact that we see a decline on the number of bars at high redshift, is that telling us that we need to have the galaxy completely settle before forming a bar? Or because, for example, you said that the gas accretion particularly produce bars and so on, and we expect more gas accretion at high redshift, or at least the star formation is higher. So what can you say about that?
Well, if the ability of a galaxy to regenerate a bar depends on gas accretion, then in principle it could go through many episodes, and the bars that we see today could be many bar episodes later. How many is hard to say, but I could certainly see that. In these high luminosity galaxies, the bars are supposed to form quickly, but I could certainly see at high red shift that this cycle could be faster, and and the bars that we see today could be many bar episodes later. I could see that. I don't know how you prove it, but because the bars generally have an old stellar population, and I don't recall what the colors of these high red shift bars are, whether they're all red or some are blue. But of course, we find blue bars even nearby. So the process is going on today, perhaps at a lower level. But I could see that we're many bar generations later if that's really happening.
Okay, no more questions then? Thank you very much for your talk.
Thank you.